When France signed the armistice at Compiègne on the 22nd of June 1940, Grand Admiral Eric Raeder saw something Winston Churchill desperately feared: 1,000 kilometers of Atlantic coastline suddenly under German control. The Kriegsmarine had just gained the most valuable real estate in the entire European theatre, and they knew it within hours of the surrender. Before France fell, German U-boats operated from bases in Wilhelmshaven and Kiel, ports tucked away in the Baltic and North Sea. Every patrol meant a grinding 7-day journey just to reach the Atlantic hunting grounds where British convoys sailed. 7 days out, perhaps 10 days on station if fuel allowed, then 7 days back. The mathematics were brutal. A Type 7 U-boat spent more time transiting than actually sinking ships, and the Royal Navy's destroyers controlled the choke points around Scotland and through the English Channel. The French Atlantic ports changed everything overnight. Lorient, Saint-Nazaire, Brest, La Pallice, Bordeaux, these weren't just harbours. They sat directly on the Atlantic, shaving 2 weeks off every patrol cycle. A U-boat commander could now spend 3 weeks hunting convoys instead of 10 days. The operational efficiency gain was staggering, effectively tripling the Kriegsmarine's submarine presence in the Atlantic without building a single additional boat. Admiral Karl Dönitz, commander of the U-boat fleet, moved his headquarters from Wilhelmshaven to the Villa Carillon in Lorient by September 1940. He wasn't being theatrical. The man understood that proximity to his operational boats meant faster tactical decisions, better coordination of wolfpack attacks, and direct oversight of the campaign, strangling Britain's maritime lifeline. Every merchant ship Britain lost meant fewer tanks, aircraft, ammunition, and food reaching British soil. The strategic implications terrified the Admiralty in London. Britain imported 20 million tons of food annually, along with virtually all petroleum, rubber, and the raw materials keeping munitions factories running. The convoy system worked, barely, but now German submarines could patrol further west into the Atlantic, staying on station longer and hitting convoys earlier in their journeys. The mid-Atlantic gap, where land-based aircraft couldn't provide air cover, suddenly became a U-boat killing field. By October 1940, the first flotillas were already operating from Lorient. Type 7 sea-boats pulled into French ports after patrols, underwent rapid maintenance and torpedo reloads, then headed straight back to the convoy routes. Turnaround time dropped from 6 weeks to 2. The tonnage figures told the story. British merchant losses climbed from 200,000 tons in June 1940 to over 350,000 tons by October, and Dönitz was just getting started. The French bases offered something else invaluable: access to the Bay of Biscay's direct Atlantic routes. U-boats could slip out of Lorient or Saint-Nazaire, cross the bay in 36 hours, and reach the western approaches where convoys bunched together before dispersing. No more squeezing through the Dover Straits or risking the Scotland passages where British destroyers waited with ASDIC sets pinging. But Dönitz and Raeder both recognised the vulnerability immediately. These Atlantic bases were now Germany's most precious naval assets, and the RAF would come hunting. The admirals needed protection, serious protection, because if Bomber Command destroyed the facilities or rendered the harbours unusable, every operational advantage evaporated. The submarines needed somewhere bomb-proof to shelter, refit, and reload safely. Organisation Todt was about to receive the most demanding construction brief of the entire war. Organisation Todt mobilised 15,000 workers by February 1941. Fritz Todt himself approved the designs, reinforced concrete structures engineered to withstand anything the RAF could drop. The specifications were extraordinary, roof sections ranging from 3.5 meters thick at the thinner installations to 7 meters at facilities like Keraman 3 in Lorient. 7 meters of steel reinforced concrete. The engineers genuinely believed they were building structures that physics itself would defend. The construction followed a brutal timeline. At Lorient, the Keraman complex eventually comprised 3 separate bunker facilities. Keraman 1 opened in February 1941 with 5 pens, each capable of sheltering a Type 7 U-boat. Before the concrete fully cured, Organisation Tot was already pouring foundations for Keraman 2, which added 7 more pens by October 1941. Keraman 3, the largest, wouldn't finish until January 1943, but when completed it housed 13 pens under a roof slab that weighed over 200,000 tons. Saint-Nazaire's submarine base matched Lorient's ambition. The complex featured 14 pens, with the roof reaching 6.5 meters thick in sections. The individual pen chambers measured 15 meters wide and over 180 meters long. Cavernous spaces where U-boats could dock entirely undercover. Maintenance crews worked beneath the concrete canopy, loading torpedoes and conducting repairs whilst RAF bombers circled overhead, unable to touch them. Brest received its bunker complex by October 1941, though the design differed slightly. The Brest pens incorporated 15 individual berths, but engineers added massive blast doors at the seaward entrance, steel gates weighing hundreds of tons that could seal the facility completely. The doors themselves were 3 meters thick, armoured enough that engineers calculated they could withstand direct torpedo hits from British midget submarines if any penetrated the harbour defences. La Pallice, serving La Rochelle, and the Bordeaux facilities followed similar principles, but on slightly reduced scales. La Pallice's bunker featured 10 pens with roof thickness reaching 4.5 meters, whilst Bordeaux's complex at Bacalan housed 13 U-boats beneath 5 meters of reinforced concrete. Each facility included internal workshops, electrical substations, torpedo storage magazines, crew quarters, and command centres, fully functioning submarine bases that could operate indefinitely under aerial attack. The concrete itself represented a specific engineering calculation. Standard RAF bombs in 1941 were the 1,000-pound general purpose and the 2,000-pound semi-armour piercing variants. Both relied on explosive blast effect rather than penetration. German engineers calculated terminal velocities, explosive forces, and conducted tests against mock-up roof sections. Their mathematics showed that even a 2,000-pound bomb dropped from 6,000 meters would penetrate perhaps 1 meter into properly reinforced concrete before detonating. The blast would crater the surface, certainly, but wouldn't compromise structural integrity. They added steel reinforcement in double layers, horizontal rebar grids spaced every 30 centimeters throughout the concrete depth, with vertical reinforcement columns every 2 meters. The roof sections were poured in segments but engineered as continuous slabs, so localized damage couldn't trigger progressive collapse. Drainage systems channeled away water from bomb craters. Ventilation shafts were protected by chicanes and blast baffles. The Germans thought of everything. Labour came from multiple sources. Some French workers accepted wages, others worked under compulsion, and thousands of prisoners of war and forced labourers poured concrete under armed guard. The construction consumed staggering resources, over 500,000 cubic metres of concrete just for the Lorient facilities alone, requiring continuous cement shipments that strained German logistics. By mid-1942, the bunker network was largely complete, and Dönitz's submarines had fortress protection. The Admiral confidently predicted the RAF would exhaust itself trying to crack his concrete shields. Bomber Command was about to prove him correct, at least temporarily. Bomber Command sent 216 Wellingtons, Halifaxes and Stirlings against Lorient on the night of the 13th of January 1943. The raid was the culmination of 18 months of increasingly desperate attacks against the U-boat pens. By dawn, reconnaissance photographs showed cratered dockyard facilities, destroyed warehouses and the town of Lorient itself burning. But the submarine bunkers remained untouched. Not a single pen was out of operation. The attacks had started cautiously in 1941, with small formations dropping 1,000-pound general-purpose bombs. These weapons were essentially thin-cased cylinders filled with amatol explosive, designed to destroy buildings and infrastructure through blast effect. Against 5 meters of reinforced concrete, they were pathetic. Bombs struck the roof, detonated on impact, and gouged craters, perhaps half a meter deep. Repair crews filled the holes with fresh concrete within days. Air Marshal Arthur Harris, appointed Commander-in-Chief of Bomber Command in February 1942, escalated the campaign. He authorized use of the 2,000-pound semi-armor-piercing bombs, weapons with thicker cases designed to penetrate before exploding. The theory was sound. The hardened steel nose would bite into concrete, the bomb would penetrate deeper, and the delayed action fuse would trigger the explosion inside the structure rather than on the surface. Reality disappointed. The SAP bombs penetrated perhaps 1 meter into the concrete before detonating, creating deeper craters, but still nowhere near the 3 to 7 meters needed to breach the roofs. German engineers had calculated the safety margins correctly. The bombs simply lacked the kinetic energy and structural strength to punch through that much reinforced concrete, even when dropped from 7,000 meters at terminal velocity. The cost was staggering. Between January 1942 and January 1943, Bomber Command flew over 3,000 sorties against the French U-boat bases. They lost 96 aircraft and over 600 aircrew killed or captured. The Germans lost not a single submarine to direct bombing inside the pens. Not one. Saint-Nazaire received particularly heavy attention. 173 bombers on the night of the 16th of February 1943. Another 211 on the 28th of February. The town was obliterated, thousands of French civilians killed, but photographs showed U-boats still sheltering safely inside the bunkers. The concrete roofs bore pockmarks and crater scars like some ancient battlefield, yet structurally remained sound. Wing Commander Gay Gibson, later famous for the Dams raid, participated in several attacks on Brest in early 1942, whilst commanding 106 Squadron. His combat reports reflect mounting frustration. Accurate bombing runs, bombs observed, striking the target area, then reconnaissance showing the pens, quote, undamaged and operational. The crews were risking their lives hitting a target they couldn't actually hurt. The Admiralty pushed Bomber Command relentlessly. Every U-boat sailing from those bases meant British merchant ships sinking in the Atlantic. In November 1942 alone, U-boats sank 119 Allied vessels, totaling over 700,000 tons. The pressure to destroy the bases, or at least render them unusable, was enormous. Harris tried different tactics. He ordered maximum concentration raids to create rubble and debris that might block the pen's entrances. Bombers dropped 4,000-pound cookie blast bombs designed to destroy everything within enormous radius through sheer overpressure. These weapons devastated surrounding areas, but the bunker entrances featured massive blast doors and chicane designs that channeled shockwaves harmlessly away. By spring 1943, senior RAF officers privately acknowledged Conventional bombing couldn't crack the pens. The concrete was simply too thick, and current weapons too light. The Kriegsmarine had built structures that existing bombs couldn't defeat. Britain needed something revolutionary, a weapon operating on entirely different principles. Fortunately, one engineer had already started designing exactly that. Barnes-Wallis had already proven himself impossible to dismiss. On the 17th of May 1943, his bouncing bombs breached the Murner and Eder dams in a single night, validating engineering calculations so precise that senior Air Ministry officials, who'd previously called him a dreamer, now hung on his every proposal. When Wallis suggested he could crack the U-boat pens, people listened. The Vickers-Armstrong's engineer had actually been working on deep penetration bomb theory since 1941, well before the dams raid made him famous. His initial paper, a note on a method of attacking the Axis powers, calculated that a 10-ton bomb dropped from 12,000 meters could penetrate 30 meters into Earth before exploding. The resulting underground detonation would create what Wallis termed a camouflet, essentially an earthquake effect that shattered structures through seismic shockwaves rather than surface blast. The physics fascinated him. Conventional bombs relied on explosive force at or near the surface, creating pressure waves that dissipated rapidly in open air. Most energy wasted itself, blasting atmosphere. But a bomb that penetrated deep before detonating would transmit shockwaves through the surrounding medium, whether earth, concrete or water, with devastating efficiency. The denser the medium, the better the energy transfer. Wallis calculated that penetration depth depended on three critical factors: bomb weight, impact velocity, and structural integrity of the casing. Standard bombs tumbled during descent, presenting variable cross-sections to the airstream and losing velocity. They struck targets at perhaps 240 meters per second, fast, but not enough to punch through serious concrete. Their thin cases crumpled on impact, triggering the fuse before achieving deep penetration. His solution required rethinking the entire weapon. First, make it streamlined. A perfect teardrop shape with stabilizing fins, ensuring nose-first impact every time. Second, make it enormously heavy. The greater the mass, the greater the kinetic energy at impact. Third, construct the casing from special alloy steel, thick enough to survive the tremendous impact forces without shattering. The bomb would function like an artillery shell, relying on velocity and mass to drive itself deep into the target. The numbers he calculated bordered on absurd. A 12,000-pound bomb, 6 tons, dropped from 6,000 meters, would strike the ground at over 340 meters per second, approaching the speed of sound. At that velocity, reinforced concrete behaved almost like a fluid. The bomb would penetrate not by crushing concrete, but by creating a temporary cavity, as the material flowed around the weapon's streamlined body. Think of diving into water from extreme height, the displacement rather than destruction. Then came the earthquake effect. Once embedded deep in concrete or earth, the bomb would detonate. In conventional surface blasts, most energy escapes into the atmosphere. Underground detonation trapped that energy, forcing it into the surrounding material. The shockwave would reflect off free surfaces, like the bottom of the concrete roof and the ground below, creating standing waves that literally shook structures apart from inside. Wallis tested scale models in his garden at Effingham, much to his neighbours' confusion. He dropped wooden bombs into soil and measured crater depth versus impact velocity, refining his equations. He calculated the exact fin angle needed for stable descent, the optimal explosive-to-casing weight ratio, and the precise nose cone geometry for maximum penetration. The Air Ministry remained sceptical. They'd just approved his bouncing bomb after years of resistance, and now he wanted £12,000 penetration weapons? The Lancaster bomber's maximum bomb load was £14,000, with modifications, meaning each aircraft could carry exactly one of Wallace's proposed weapons. The cost per sortie calculation looked terrible compared to conventional raids, dropping dozens of smaller bombs. Wallace countered with cold mathematics. Bomber Command had already lost nearly 100 aircraft attacking the pens with conventional weapons. 0 results. His weapon needed perhaps 30 accurate hits to destroy all facilities. 30 sorties versus 3,000. The numbers spoke for themselves. Vickers-Armstrongs received the production contract in September 1943, but manufacturing a 6-ton bomb required engineering solutions that didn't exist in any handbook. The casing alone demanded special treatment. Standard bomb-grade steel would shatter on impact at 340 meters per second. The company's Sheffield works developed a chrome-molybdenum alloy hardened through heat treatment, creating casings that could withstand impact forces exceeding 15,000 pounds per square inch without fracturing. The bomb measured 6.4 meters from nose to tail fin, with a maximum diameter of 96 centimeters at the widest point of its streamlined body. That teardrop shape was critical. Wind tunnel testing at the Royal Aircraft Establishment showed that even slight deviation from the calculated profile would cause tumbling during descent, destroying accuracy and drastically reducing penetration depth. Each bomb was essentially a precision-machined penetrator with an explosive filling, not a simple container of explosives. The tail assembly featured 4 offset fins angled to induce a slow rotation during descent. Wallace borrowed this principle from rifled artillery. The spin stabilized the weapon's trajectory and ensured nose-first impact regardless of crosswinds or release turbulence. The fins were welded to a cast steel tail section, then the entire assembly balanced to within ounces to prevent wobble. For explosive fill, Wallace specified Torpex, a mixture of RDX, TNT, and powdered aluminium that was 50% more powerful than standard TNT. The Tallboy carried 5,200 pounds of Torpex, less than half the weapon's total weight. That ratio shocked conventional bomb designers who typically maximized explosive content, but Wallace understood the physics. The casing's structural integrity mattered far more than explosive volume because the penetration depth determined the weapon's effectiveness. A light bomb with maximum explosive that shattered on impact was worthless. A heavy penetrator with moderate explosive that reached deep before detonating was devastating. The fusing system required particular cleverness. Standard impact fuses would detonate the bomb the instant it struck concrete, defeating the entire purpose. Wallace designed a delayed action fuse that armed during descent but only fired after a programmed delay following impact. The bomb would punch through concrete. The delay mechanism would count microseconds, then detonation would occur when the weapon had penetrated maximum depth. Fuse testing involved dropping prototype bombs into quarries filled with graduated concrete slabs. Lancaster bombers needed substantial modification to carry Tallboys. The standard bomb bay doors were removed entirely, and the bay itself bulged outward with a streamlined fairing to accommodate the weapon's diameter. Hydraulic systems were upgraded because hoisting a 6-ton bomb into position required lifting capacity far beyond original specifications. Avro's engineers reinforced the bomb bay beams and fuselage structure to handle the concentrated weight distribution. But the truly demanding challenge was crew training. Dropping Tallboys required altitude, minimum 5,500 meters, to achieve necessary impact velocity, ideally 6,000 meters or higher. At that altitude, bombing accuracy with standard techniques was atrocious. Crews needed to stabilize the Lancaster absolutely straight and level. During the final approach, maintain precise airspeed and release at the exact calculated moment whilst heavy flak burst around them. 617 Squadron formed in April 1943 under Wing Commander Guy Gibson, specifically for precision raids with special weapons. After the Dams raid, Gibson's departure for a publicity tour led Squadron leader George Holden to command, then Wing Commander Leonard Cheshire, in November 1943. Cheshire revolutionized their tactics, developing low-level marking techniques where he'd dive to under 100 meters, mark targets with flares despite intense anti-aircraft fire, then high-flying Lancasters would bomb the marked point from altitude. This combination of suicidal courage and mathematical precision transformed what Tallboys could achieve. The raid on Lorient's Keraman Pens launched on the 27th of June 1944, 3 weeks after D-Day, when Allied air superiority over France was absolute. Cheshire led 16 Lancaster bombers from 617 Squadron, each carrying a single Tallboy. The timing was deliberate. German forces were reeling from the Normandy invasion, air defences stretched thin, and the U-boat pens had become even more critical as Allied naval forces tightened their grip on French Atlantic ports. Cheshire took off first in his personal Mosquito, a fast, manoeuvrable twin-engine aircraft perfect for low-level marking runs. The plan was vintage Cheshire. He would go in low, mark the target with smoke bombs whilst evading flak. Then the Lancasters at 6,000 meters would bomb his markers. The technique exploited Tallboy's unique characteristics. Even near misses could work, because the weapon penetrated earth beside the structure and triggered underground shockwaves. The Mosquito crossed the French coast at 200 meters, hedge-hopping to avoid radar detection. Cheshire identified Keraman 3, the massive complex with 13 pens and that 7-meter thick roof that had laughed at hundreds of previous raids. He pulled into a shallow dive, accelerated to over 500 kilometers per hour, and released his red target indicators directly onto the bunker's roof, whilst 88mm flak batteries tracked him desperately. 6,000 meters above, Flight Lieutenant John Cockshott watched the red smoke billow across Keraman's concrete expanse. The sight picture was perfect. Clear June weather, smoke marking the exact aim point, and 15 Lancasters queuing behind him in trail formation. He steadied his bomber, the bomb aimer called corrections, and at precisely the calculated release point, the Tallboy dropped away. The weapon fell for 43 seconds. To observers on the ground, it appeared as a dark streak accelerating downward, the offset fins spinning it into a stabilized trajectory. Impact velocity exceeded 340 meters per second, over 1,200 kilometers per hour. The Tallboys struck Keraman 3's roof approximately 6 meters from where Cheshire's smoke markers burned. What happened next stunned German engineers monitoring from nearby shelters. The bomb didn't bounce or shatter. It punched through 7 meters of reinforced concrete as though the material was packed sand. The penetration lasted perhaps 0.2 of a second, not an explosion, just the physical displacement of concrete around the weapon's streamlined body as kinetic energy drove it downward. Then the delayed fuse fired. 5,200 pounds of Torpex detonated inside the concrete roof slab. The explosion couldn't escape upward or sideways. 7 meters of concrete trapped the blast. Instead, energy transmitted through the structure as a compression wave travelling at over 5,000 meters per second. The shockwave reflected off the bottom surface of the roof, bounced back from the ground below, and created standing interference patterns that literally vibrated the concrete apart from inside. The roof didn't crumble gently. A section 20 meters across collapsed catastrophically, dropping hundreds of tons of shattered concrete into the pen below. 2 Type 7 U-boats were crushed instantly. A third sustained damage so severe it would never sail again. The cavernous interior space that had protected submarines through years of conventional bombing had become a tomb in less than 1 second. 14 more Tallboys followed. Not all struck the roof directly. 3 hit the surrounding dock area, 2 landed in the harbour waters adjacent to the bunker. But those near misses proved Wallace's earthquake theory spectacularly. The bombs buried themselves 6 to 8 meters into earth and concrete aprons before exploding, sending shockwaves rippling through the ground that cracked the bunker's foundation walls and twisted support columns. By the time the last Lancaster turned for home, reconnaissance photographs showed Kerriman 3 with multiple roof breaches, collapsed internal structures, and damage the Germans had previously considered physically impossible. German naval engineers arrived at Kerriman within hours of the raid, and their reports betrayed genuine disbelief. Korvettenkapitän Helmut Brummer-Patzig, responsible for bunker maintenance, documented penetrations reaching 6.2 meters into concrete that calculations had proven impenetrable. His technical assessment noted that conventional bomb craters typically measured 1 to 1.5 meters maximum depth before explosive force dissipated through fracture patterns. These Tallboy impacts showed smooth penetration channels extending far deeper, with the explosive detonation occurring entirely inside the structural mass. The damage mechanism was unlike anything they'd encountered. Surface cratering from conventional bombs created localized destruction. Repair crews simply filled holes and carried on. Tallboy penetrations created internal cavities, where Torpex detonated under enormous confining pressure. The blast energy couldn't escape, so it propagated through the concrete as compression waves. Those waves encountered the reinforcement bar matrix and reflected at every steel-concrete interface, creating thousands of individual fracture points simultaneously throughout large volumes of the structure. The roof collapse at Kerriman 3 revealed something else disturbing: progressive failure. One section's collapse created stress concentrations in adjacent sections. Reinforcement bars that survived initial blast loads failed hours later under redistributed weight they weren't designed to carry. By the morning of the 28th of June, 2 additional roof sections showed alarming crack patterns and had to be evacuated. The bunker was eating itself. St. Nazaire received 617 Squadron's attention on the 9th of August 1944. Cheshire marked the target again, and 19 Lancasters delivered their Tallboys with precision that horrified the German garrison. 4 bombs achieved direct roof penetration. One struck the massive seaward blast door and punched completely through 3 meters of armoured steel before exploding inside the entrance chamber. The door, those hundreds of tons of steel the designers had calculated could withstand direct torpedo strikes, was torn from its hinges and twisted into scrap. The blast door failure proved particularly catastrophic because it compromised the bunker's entire defensive concept. The structure was designed as a sealed fortress. The doors maintained internal atmospheric pressure during raids, protected against fragmentation, and allowed submarines to shelter during air attacks. With the entrance breached, blast effects from subsequent conventional bombing could propagate inside. The pens became a liability rather than protection. Submarines risked being trapped inside a damaged structure. Brest's turn came on the 6th of August, with similar results. Reconnaissance photographs showed 3 separate roof breaches, collapsed sidewalls in 2 pens, and the rail-mounted crane system, essential for loading torpedoes, destroyed beyond repair. German damage assessments calculated 4 to 6 months minimum repair time, assuming resources and labour could be diverted from increasingly desperate defensive positions along the Atlantic Wall. What terrified Dönitz and his staff was the efficiency. Bomber Command wasn't carpet bombing anymore. gambling on statistical probability that something might damage the pens. 617 Squadron was conducting surgical strikes with weapons purpose-designed to defeat reinforced concrete. The mathematical certainty that had underpinned bunker construction, those calculations proving standard bombs couldn't penetrate, had been rendered obsolete by a weapon operating on entirely different physical principles. La Palisse received attention on the 9th and 10th of August, with Tallboys collapsing 2 pens and severely damaging 3 others. By mid-August 1944, every major U-boat bunker on the French Atlantic coast had sustained significant damage. Some remained partially operational, but the invulnerability was gone. U-boats could no longer shelter with absolute confidence, and maintenance schedules were disrupted by the constant need to relocate boats away from damaged sections. The engineering certainty that concrete alone could defeat aerial bombardment had shattered as completely as the bunker roofs themselves. Dönitz faced a crisis that logistics alone couldn't solve. By September 1944, his Atlantic bases, the strategic treasure that France's fall had gifted Germany, had transformed from force multipliers into operational liabilities. U-boats returning from patrol couldn't risk extended stays in damaged pens where roof collapses might trap them, and the rapid turnaround times that had made French bases so valuable evaporated as submarines dispersed to improvised facilities. The dispersal revealed itself in intelligence intercepts and patrol reports. U-boats that previously docked at Lorient for streamlined maintenance now scattered to smaller ports along the Biscay coast. Royan, La Rochelle's outlying harbours, even desperate attempts to use river facilities inland where Tallboys couldn't reach. But these locations lacked the infrastructure. Torpedo reloads that took 12 hours at properly equipped Keraman pens now required 3 days, using makeshift derricks at secondary harbours. Diesel engine overhauls that specialised workshops completed in 5 days stretched to 2 weeks. The mathematics were crushing. A Type 7C U-boat in mid-1943 typically spent 10 days in port between patrols, refuelling, rearming, repairs, and crew rotation. By late 1944, with bunkers damaged and crews dispersed to inadequate facilities, turnaround times averaged 23 days. Dönitz was effectively losing half his operational submarine force to maintenance delays caused not by mechanical failures but by Tallboy-induced infrastructure destruction. Allied intelligence tracked the degradation through ultra-decrypts of Kriegsmarine signals. Desperate German messages, detailed parts, shortages, inexperienced repair crews, fumbling tasks that veteran Lorient technicians had perfected, and submarines forced to sail on patrol with incomplete maintenance because staying in port risked being caught during the next RAF raid. Several U-boats sailed with malfunctioning diesel engines or faulty torpedo tubes, defects that would never have passed inspection in 1942, but were now considered acceptable risks. The strategic timing amplified the disaster. By late 1944, Allied escort carriers, improved sonar, airborne radar, and lee lights had already tilted the Atlantic battle decisively against U-boats. The period historians call Black May of 1943, when Dönitz lost 43 submarines in a single month, had forced tactical retreats and equipment upgrades. Schnorkel devices allowed underwater diesel operation, acoustic homing torpedoes, targeted escorts, and new Type 21 submarines promised revolutionary underwater performance. But those innovations required functional bases to deploy effectively. Type 21 boats, with their sophisticated equipment and higher crew skill requirements, needed proper shipyard facilities for shakedown and training. Schnorkel-equipped boats required careful maintenance of the breathing masts, delicate valve mechanisms, work impossible in improvised harbours. The technological solutions Dönitz hoped would revive his Atlantic campaign founded against the simple reality that Tallboy had eliminated the infrastructure needed to support them. British merchant ship losses reflected the strategic shift dramatically. In 1942, U-boats sank over 7.8 million tons of Allied shipping, an average of 650,000 tons monthly. By the final quarter of 1944, monthly losses had collapsed to under 80,000 tons, and U-boats accounted for decreasing percentages as mines, aircraft, and operational accidents became proportionally more significant. The bunker destruction didn't sink submarines directly. No U-boat was lost to Tallboy impact whilst at sea, but the weapon achieved something perhaps more devastating. It shattered the operational system supporting the submarine fleet. Every additional day, a U-boat spent in port awaiting repairs or hiding in inadequate facilities was a day it wasn't sinking Allied ships. The Tallboy raids represented something unprecedented in aerial warfare, the deliberate application of physics and engineering principles to defeat a specific defensive technology. Previous bombing doctrine had relied on overwhelming volume. Drop enough explosives and probability alone would eventually destroy any target. Barnes-Wallis demonstrated that understanding the target's vulnerabilities could achieve with 30 sorties what 3,000 conventional raids couldn't accomplish. The immediate lesson wasn't lost on either side. Germany's organisation TOT began designing bunker roofs with void spaces, layered concrete separated by air gaps, intended to absorb penetration energy before bombs reached critical depths. These designs appeared in V-weapon launch facilities constructed through late 1944, though material shortages and Allied advances meant few were completed. The principle was sound. If Tallboy defeated concrete through kinetic penetration, then multiple separated layers might break up that penetration before the weapon reached detonation depth. Britain developed the concept further with Grand Slam, Wallace's even larger penetration bomb weighing 10,000 kilograms. 617 Squadron dropped these weapons against U-boat pens at Farge and the Valentin submarine bunker near Bremen in March 1945. The Valentin bunker featured a roof 4.5 meters thick with an air gap and secondary roof layer. Grand Slam penetrated the entire assembly, detonated deep inside the structure, and caused collapses that rendered sections of the facility permanently unusable. Post-war analysis by Allied bomb damage assessment teams revealed fascinating details. At Kerriman 3, engineers excavated Tallboy impact sites and measured actual penetration depths against Wallace's theoretical calculations. The correlation was remarkable. Predicted depths matched observed depths within 15 centimeters across multiple impacts. The man's mathematics had been essentially perfect, validating his theoretical framework for projectile penetration into dense media. The United States Army Air Forces studied Tallboy results intensively whilst developing their own bunker-busting weapons. The VB-13 Tarzan, a 12,000-pound bomb with radio guidance, borrowed Tallboy's streamlined shape and hardened casing principles. Later American weapons like the BLU-109 bunker buster and its successors employed identical physics. Maximize kinetic energy through weight and velocity, use hardened penetrator casings, detonate only after achieving maximum depth. Cold War strategic planning absorbed the lessons completely. Soviet bunker construction in the 1950s featured massive concrete protection for command centers and missile silos. But Western military planners countered with increasingly sophisticated penetration weapons. The B-61 nuclear gravity bomb, America's primary strategic weapon, through the 1960s, featured a hardened case specifically designed for Earth penetration before detonation, creating underground nuclear explosions that could destroy deeply buried facilities through seismic shockwaves. Wallace's earthquake effect scaled up to nuclear yields. The tactical revolution extended beyond weapons to target selection and mission planning. Precision bombing doctrine, striking specific aim points with purpose-designed weapons rather than area saturation, became fundamental to Western air power philosophy. The concept that emerged from 617 Squadron's raids on French U-boat pens evolved into the precision strike capabilities defining modern air warfare. Perhaps the most significant legacy was conceptual. The understanding that defensive technologies always contain inherent physical limitations, and that rigorous analysis could identify exploitable vulnerabilities. The Germans built bunkers, assuming bombs would always detonate on impact with limited penetration. Wallace simply asked what would happen if the bomb didn't detonate on impact, penetrated deeply instead, and exploded from inside the structure. That question, combined with the engineering brilliance to transform theory into functional weapons, broke the seeming invulnerability of reinforced concrete fortifications. The U-boat pens at Lorient still stand today, 70 years later, massive concrete ruins, testament to both German engineering ambition and the British innovation that defeated it.